recording first and then share screen. Okay. As I said, thank you for being here for this second tutorial of the diiP tutorial series. In this one, we're going to give an overview of deep learning. And as an example, we'll use a simple deep learning model, which is called multilayer perceptron. Okay. Excuse me. Oh, here it is. So the outline is of the talk, we're going to describe what is deep learning in high-level terms. We'll talk a little bit about tensors, which is the main data structure that is used in deep learning. We'll say what is a tensor and how it is used. Then we'll introduce the multi-layer perceptron, and with this we'll start describing how do you train how models in deep learning look, how do you train them. We'll get into some details on training the models with deep learning models and specific topics like regularization, which is important for training and good performance for these models. And I'll give you some examples of deep learning toolkits and libraries, which it's not by no chance complete, but some of them are popular, some of them are descriptive of the field. And as I said, we'll have a small example or demo, how you want to call it, of a prediction example using the multi-layer perceptrons. Let me move this here. Okay. So deep learning is a field in machine learning. First of all, I assume that everybody knows what is machine learning. I'll give a very short overview. Machine learning is a field in artificial intelligence that contains algorithms or methods to learn from the data, to learn different patterns from the data. Usually in computer science, you have an algorithm that you describe how to do something, while in machine learning, the model or the algorithm learns that these patterns, these rules, this process through the data. And part of this machine learning is the deep learning, with another field in machine learning that is concerned with algorithms based on what we call artificial neural networks, and we see the structure of these models, and representation learning. So the artificial neural networks provide the computation backbone to construct deep learning models. Basically, it's using neural networks, we create these deep learning models, and representation learning involves to automatically find an appropriate representation of data in order to perform an ML or AI task. Here, we're not going to discuss representation learning, but I'll give you an example. Assuming that you have unstructured data, that you get images and you want to classify them. For example, you have images of planes and cars. So your input is this unstructured thing, bits and bytes, how it is described, how an image, a colored image is described in a computation form, and you want to be able to identify, to say, oh, this particular image is an image of a car, and this particular image is an image of a plane. So representation learning is using algorithms, different algorithms that identifies create structure in this unstructured image. For example, it identify edges, colors, distribution of edges, distribution of colors, start shapes, and so on. And this happens without human intervention. And this is a big thing in representation learning. And a part of, in deep learning, part of success is this. Okay. Now, a deep learning model is, as any other model, is a mapping, is a function that maps inputs and inputs that your independent variables to outputs, and that's your dependent variables. And this function is usually parameterized with a set of parameters. And as part of the training or learning in a deep learning model, you instantiate these parameters. And what you try to do is that part of the training, the optimization that you do in order to identify these parameters, is to find the set of parameters that gives you the best approximation of this function f. Okay. And is of computation, of explanation, of for educational reasons and others. A deep learning model is usually represented with a layer-directed acyclic graph, basically a graph that does not have cycles. It's directed, that means that its edges have a direction going from one node to another. And this graph can be divided into layers, and we'll see these layers. And a node in this graph represents either a tensor or a computation over tensors. And as we said, we'll discuss what is a tensor. This is basically the structure where data is represented in deep learning. An edge represents some information flow or dependency. A layer is a set of nodes. The input layer is your input, which is again described as tensor. So you first describe your input data in the form of a tensor, and then you feed that to the deep learning model. It has 0 or more hidden layers, and what we call hidden layer here is that layers for which the output is not observed, and the output layer is the one that computes the results, the Y, as we saw in the previous slide. Okay. Now the layered graph, as we said, the deep learning model is a layered graph, and each layer describes a set of functions, and the dependency between these layers is defining a composition between functions. So, for example, here, if we assume that the output layer is computing the function f, and f1 is your input. That's a function that's represented by your input layer. Then every other layer is a composition of the function of the previous layer. So in this case, f is f3 the composition. Let's see how to see f3 composition f2 composition f1. So basically for you, how you can see it is that you get the input, and the input flows and it's transformed through its layer until it results and provides the output. Okay. Now, although this layered graph is a representation of any kind of neural network model, in deep learning, usually the number of hidden layers, what we show hidden 1 and 2, is actually large. Like it could be 20, it could be 50, it could be thousands. Okay, and that's basically, as you can see, with so many different layers, you create a composition of too many functions, and the complexity of the model is increasing. And that's basically what we see here is a comparative kind of relative comparative of deep learning, machine learning models. So we have in the lower level the traditional ML algorithms like SVM or tree-based algorithms, ensembles, so on and so forth. And then you start adding complexity based on the neural network, the layers that you have in your neural network model. Okay. Before I continue, any questions so far? No. Okay. Now let's go to see that, as we say, promised, what is a tensor. So the tensor is the main data structure for deep learning. Everything in deep learning is described as a tensor. And what's a tensor? A tensor is a container that can house data in n dimensions. Basically, you can think of it as an n-dimensional array. But as opposed to an n-dimensional array, it also contains a set of usually linear functions. Okay, so a tensor knows both the data as well as the operations that happen on that structure. For example, a tensor can find the transpose of itself, or a tensor can compute the gradient of the function where this tensor exists at any given point. So as far as data as we said, you can you can think of the tensor as a multi-dimensional array. So every tensor has a name. That's the variable name that we give. The rank, which is how many axes it is, the shape, how many elements it has in a dimension, and the data type. And the data type is what kind of types the element in each cell in the tensor has. It could be floating, integers, doubles, and so on and so forth. So as an example, the tensor that we have in the lower part of the slide, it is a tensor that I call it A. It's of integer type because you see every element there is integer. The rank is 2 because there are 2 axes. And the shape, which is, as we said, the number of elements that is its axis 4 by 5. So 4 elements in the one axis and 5 elements in the other axis. Okay, so some real-world examples of tensor. Basically, tensor series is data described with tensor. Stock prices, we can represent stock prices with a present. For example, for every minute, we store the current price of the stock, the highest price of the past minute, and the lowest price of the past minute. In this case, we have all the data in one tensor, which has a shape 390. That's how many minutes we have. And 3, it's the 3 different metrics that we said that we keep. That is the lowest price, the highest price, and the price of the stock. Okay. In images, which is typical used for, you usually see images more in everyday life, and we usually see them in tensors. The images usually have 3 dimensions. That's the height, the width, and the color depth. How many color channels? Usually 1 if it's a grayscale image, 3 if it's a colored image. And assuming that we have an image of size 256 by 256, this can be stored, and that's a grayscale image, can be stored in a tensor of shape 256 by 1, and because we can have as many dimensions as we want, we can store all the images, say that we have 128 on the same tensor, in which case the tensor is going to be 128 by 256 by 1. Okay. And video data. A video is usually a sequence of frames, and each frame being a color image. So say that we have a number of videos that we want to be stored, then the tensor that we're going to say is how many, the number of videos, the number of frames per video, the height, the width, and the color depth of the of its frame. So this is going to be a tensor of rank 5.
Excuse me, I have a question.
Yes.
Why we need to use tensor instead of array? Because I think array can do almost everything, just like tensor.
Yes, that's why I said the tensor. You can think of it as a multi-dimensional array when it comes to the data. But then the tensor also has it has as we said, a set of functions that can be defined on that. Basically, a tensor, under the covers, both may be implemented the same or similar ways, but the abstraction that the deep learning community for storing data is the tensor. Okay. But when it comes to data, you can think of them that, oh yeah, the abstraction is the same. Now, when we said like some additional functions, like for example, we'll see later that we need to compute some gradients, the tensor knows how to compute the gradient of the function on the point that is described by the tensor, while the array that doesn't have this notion. Okay, so you can think of it as a more extended array. Although, as I said, the underlying implementation may be similar but different. Okay.
Okay, thank you.
Any other question? Now we stop. Okay. Okay, so having said that, so we'll see the multi-layer perceptron, which is a very similar notion as we saw with the. It's actually exactly what we said. It's a layered. a cyclic graph, a directly acyclic graph. The different names for multi-layer perceptrons is feed-forward neural networks, and is the simplest and very important deep learning model. And every multi-layer perceptron consists of a set of perceptrons that are stuck together in several layers. So all these the layers is exactly what we described in the layered acyclic graph. And the function at this layer is defined by the set and of the perceptrons at that layer and the computation that happens at that layer. Okay, and we'll see what is this computation. But before, let's talk a little bit what is this layer. So here, in this example, you can think of a perceptron as one node. The nodes here describe perceptrons. Okay. And one more thing also is that the feed-forward network of the multi-layer perceptron, the output of every perceptron of one layer is fed to every other perceptron in the next layer. As you'll see here, the perceptrons at the input layer, say input *1, is fed in the layers, in the perceptrons of this hidden layer, all the perceptrons of the hidden layer. Okay. And that's basically the characteristic of the multi-layer perceptron. Okay. Okay. Now, what is a perceptron now? A perceptron is a function. It's a non-linear, almost linear function that gets as input a set of numbers and computes the weighted sum of these numbers. And then this weighted sum is fed through a function, a nonlinear function, which we will call it activation function. And this function, in the original non-activation function, was here, what we call, sorry, let's see, the sigmoid function, which basically, as it says here, it gives the number 1, it produces 1 if the weighted sum is greater than some threshold, and excuse me, let's see, 0 otherwise. And it is a continuous function, the sigmoid function. Okay, and also just say something here is that you can also, the inputs describe some factors, your independent variables, but it can also have a bias, what I show here with the red arrow, the bias, which tries to model unobserved factors or factors that you haven't taken into consideration in your model, all the rest of the world, okay? As we said, the sigmoid function, it was one of the first functions that were used, but there are other ones, and we'll see. Now, let's go a little bit here. As we said, so every one of we said here the nodes is a perceptron, and its layer is described by a set of perceptrons. Now, the weights of its layer can be described by a matrix. As we saw, every perceptron gets a vector of weights, which is equal to the number of the inputs. You have one weight for the input, and then you have a set of perceptrons, so you can describe this way, all the weights in the form of a matrix. And what I want to say here is that when you talk about, when you try to create a perceptron, try to code a perceptron through a library, and it says what the weights of this particular layer, it describes this matrix. Okay, is this clear? It's more of there's nothing more new there, except it's more like a notation. Okay. Now, applications of the multi-layer perceptrons, they create competitive predictive models. So for tabular data, and when we see tabular data, this is usually data that numerical data, integers, booleans, doubles, floats, that can be described in a tabular form. Okay, so when we have these kinds of data, which we also call them structured data, and we want to perform a prediction task, for example, classification or regression. Multi-layer perceptrons are competitive models, them and ensembles of what is called ensembles of trees. These are the two families that they are usually give you. They are usually in the top performant models. The multi-layer perceptrons are usually, almost always, part of other deep learning models. Like they are used as layer of deep learning models, and they also form the basis of many important neural network architectures that we'll see in other tutorials, for example, convolution neural networks, recurrent neural networks, and they're also the main building block of what is called the transformer network, which is a very state-of-the-art, very performant neural network, deep learning model that becomes more and more ubiquitous. Okay. Okay. Now, as we said, we talk about the activation functions in the perceptron, which we said is the function, the nonlinear function that gives the output, that produces the output. And we saw the sigmoid. There are other activation functions that are used in deep learning, namely sigmoid or logistic, same thing, tan or hyperbolic tangent, rectified linear unit or ReLU, and leaky rectified linear unit. These are the common popular activation functions, and I have here how they look for your information. Now, other ones is softmax, which is used when you have a classification problem of multiple classes. For example, as we said, we have images, and except from we have cars, planes, but we also have motorbikes. That's multiple classes because you have 3 different categories, and you want to predict each image in which category it's used. There, softmax is probably activation function or output function for the output function. No, sorry, the activation function of choice for the output. And apart from there are some that if somebody is interested, we'll look at the literature. Recently, you'll see LU and GLU. LU is exponential linear unit, GLU is Gaussian linear unit that claim and show in different cases a better performance. Now, LU is consistently more performant than the others, but it's notoriously more expensive. And LU, depending on which, right now it's more at the research academic level, you'll see more or less advantage, opinions, positive, more or less positive opinions for that. Okay.
One question. This is what I was going to ask you. If you have any comments on when do we use each one? Or, yes, how can we choose?
Okay, I will show some, but please don't take them as rules. In deep learning, there is no rules. Most of the times it will be tried. Like you can have an intuition, or there are general rules that you might use, you might have. But in the end, it's really kind of a trial and error. Okay, but I will show some for this. But I'll show for the first 4, which are more established, popular, and more. You see it more in a practical. I would say non-research works. Okay. So sigmoid and tan related functions, they're usually they have similar usages. They are usually preferred when you have binary classification, like they usually perform a little bit better. However, they're usually more expensive to compute, and they have the problem of vanishing gradients. That means that when you train your algorithm, when we'll see how you train, you need to compute the gradients, and the more the deeper your model is, the more layers you have, the more this problem becomes like the gradients become 0. And when it becomes 0, then it cannot give you an answer, and we'll see why. Rectified linear unit and ReLU are usually the most activation functions of choice, and among the two, a good starting point would be leaky rectified linear unit, because it prevents the problem of what we call dyne rectified linear unit, which is similar to the vanishing gradient one. Okay, so it's similar. It means that it becomes 0. So what happens there is that if your data is very small, then the ReLU will go 0. So when your activation function returns 0, then that means everything, its output is 0. So the model cannot learn. Okay, it's basically returning always 0. Okay. And based on this, here it summarizes exactly what I said. As a rule of thumb, and again, don't take it as a law here, is that you can begin with a ReLU, and if you see that you get that a lot of your nodes become 0, then you switch to leaky ReLU in order to avoid this problem. Okay, but again, activation functions is part of the trial and error in deep learning, and sometimes also it's a matter of preference here. Okay.
Excuse me, I have another question.
Sure, go ahead, please.
The activation functions will be used in every layer or just be used in hidden layer?
So the activation functions, we saw here, it's used in every perceptron. So if we go back, it will be used in every node. Okay.
In that case, if you use ReLU in output layer, you will never get a negative value.
Why is that?
Because the output of ReLU is maximum positive.
So when you say ReLU, which one do you mean?
I don't know, ReLU.
Hyperbolic?
No, it's a rectified linear unit.
ReLU, okay. Well, this, it will give you a number, like a non-zero number, but you don't have to use that. Like, this is an option that you can have, definitely. It will give you a number because the range is from 0 to, I remember, like, what is the ReLU? I think minus infinity.
It's infinite, right? The range. So if you have a binary classification problem and you put that thing ReLU in the output layer, can you how do you threshold the?
Yes, then it's a matter of your problem. So you'll see your range, and if the activation function, the range of the activation function does not produce the range of the output that you need, you're not going to use it. Definitely. That's constraints on the particular problem. Yes.
Thank you.
But for example, if you have, yes, a regression, you can definitely use one of them. Okay, except if you have, again, constraints that, it can start from +5 and infinity. In which case, you have to think how I'm going to create an activation function that will give me this output. Okay. Any other? Let's go before we continue on the activation functions, or so far what we discussed. No. Okay. Now, continuing what we call the model training, which is what I said is the process where it tries to find numbers of the parameters, because as we said, these deep learning models, they describe a parameterized function that identify the best approximation of the function, the underlying function. Now, the problem here is that you don't know this underlying function. So, the best approximation is going to be based on the training data that you have. Okay. Now, model training here involves determining the best set of weights for maximizing a model's accuracy for a particular task. That's how we pose the problem, or we pose the problem, and it entails defining suitable loss function. And what is a loss function here is functions that quantify how far away you are from the real values, and the real values here is your training data. So, for example, if you have a classification problem, as we said, that we have images, and we have two kinds of classes, planes and cars. The model is trying to predict this label, whether it is a plane, whether it's a car. The training data is going to be some images for which you know the labels, for the labeled images. So you have images of planes, for which you know these are planes, and images of cars, for which you know they are cars. Okay. Then the loss function, what we'll try to do is to quantify how far away you are from how far away the output of the model is from the real output. And the real output here is going to be the label for each of your training data that you have. So in our case, it's going to be the label of the images. And this is for classification. Another prediction that we have is regression. In regression, you try to predict continuous variable, double variable. Okay, say that, for example, that you want to predict demand. You are a retailer and you want to predict demand of a particular vegetable, cucumber. Okay, so your real data is historical data of cucumber demand. So you know on Monday I sold 3 cucumbers, on Tuesday 4, and so on and so forth. The model is producing these real numbers, which also have the constraint that they should be positive or 0, because your demand cannot be negative. Well, depending on how you define your problem, it could be negative, but it's assuming that it is always positive. Then the loss function is going to be how far away my predicted demand is going to be from the real demand. The real demand, again, is going to be the data that you have from historical demand of these cucumber sales. And that's what you try to quantify with the loss functions. Loss functions is, again, something that you have to define or you have to design. There are some set of not predefined, existing functions. Here I have the two very popular ones, the mean square error, which also called L2 loss or quadratic loss, and is a popular function for regression problems, the demand that we described. And as you say, it does quantify how far away the prediction X, Y, P is from the real value from the training data and historical data X, Y. And for classification problems, the cross entropy loss, which is trying to quantify how far away the distribution of labels that the model produces is how different, is from the distribution of labels of the training data. And once you defined this function, and as you see, this function is a function of all the parameters, because the y the predicted function, the yp, is a function, is produced by the model, and the model is a function of all your parameters. And once we define this loss function, we compute the minimum of this loss function. We compute the optimization problem that we have is we find the values of weights that identify the minimum of this loss function. Okay. An example of other loss functions that have been used, I have here some. As I said, as everything is a matter of trial and error, these two ones that I gave you is very popular for these problems, as well as the cross entropy loss for multiple classes, which can be directly extended. but there have also been produced other ones, like the mean absolute error also is one loss function that's used a lot in retail, for example. Okay. Before continuing, any questions here on the loss functions?
Sorry, in the cross entropy functional form that you showed before, the P is the same as the YP in above?
No, so the YP here is the predicted value, is the value that the model predicts, and the P in the cross entropy loss is the probability that you produce. Okay, so what
but that's still the outcome of the fitted model, right?
Excuse me?
That's still the outcome. So in the cross entropy loss, you're still comparing the actual, I guess, training data, the Y,
yes,
to the fitted values that the model gives you. That's
yes,
P,
but
right?
here it assumes also that the model produces probabilities. So for example, if you have a softmax, that will give you a probability, something that is between 0 and 1, and it is, you know, properties of probabilities. Does that answer your question?
Yes, thank you.
Okay, so excuse me for this. Once we have defined the model train, the loss function, and we defined our optimization problem, we need to train it. A very popular training algorithm that uses variations of gradient descent. And I'm not going to go into details of the gradient descent. I just have here a graph that shows that, assuming that you have a parabola, so here, and you try to find its minimum, and say that you start at a point showing in this black point. Then at this point, you compute the gradient of the function in this point, and the gradient tells you in which direction the minimum is. And so this is basically the main algorithm that is used, some variations of this in deep learning, and enhanced with what we call the learning rate, because this gradient does not tell you, okay, it tells you the direction, but it doesn't tell you how far at every step you should go. Am I going to go 3 points down, 4 points to the left, or anything? And that is described in deep learning with what we call the learning rate. Okay. And learning rate is part of what we call the hyperparameters of the of the model. It means it is parameters that you have to set, that you have to learn outside of the training process. You have to set it by trial and error. You have to set it by experimentation. You have to set it by specific rules that exist in the literature, and so on and so forth. Okay. Any questions on this? Okay, now once we have that, the question is, okay, now how do we compute the gradient of this this complicated model that the deep learning, the complicated function of the deep learning model describes? And this is where backpropagation comes in place. The backpropagation is an algorithm that's employed to efficiently compute the gradient of the loss function. And basically what we need to do there is we need to compute on this particular function all the partial derivatives of the loss function for every weight that we have defined in our DAG, in our directly acyclic graph that defines your deep learning model, as well as the biases that describe if you have any biases. Okay. And the backpropagation is working as with two main notions, I would say. The one is that it sees the deep learning model as a computation graph, and this computation graph is described exactly by the directly acyclic graph that I described in the beginning, where each node is a perceptron. Perceptron gets some weights, and it outputs some number based on its activation function. Okay, so the first thing you do is that you the back propagation has a forward pass that computes, that uses this DAG, this computation graph, in order to compute the loss. And the backward pass is computing the gradient of the error. And the gradient of the error, the main idea is basically the chain rule that we see in the lower part of the slide. So, for example, the partial derivative of the loss given, with regard to R. We are in the other way. The partial derivative of the loss with regard to Y, you have that, and you try to identify the partial derivative of the loss with regard to R. And this is given by the chain rule that we know. Okay. So it is a kind of a semi-complicated algorithm, but it's really at every point it's using this chain rule. Every point is every node in the deep learning model in order to translate from the derivative with regard to the output going to the derivative with regard to the input of the node. Okay. One thing about this algorithm, though, is that although it is complicated because your function is, your computation graph is large, we don't need to compute it because all the libraries basically is computing that automatically. And that's part what we said about the tensors. Is the tensor, it's a tensor here is the structure that defines the data at every node, at every time, knows how to compute that the gradient of the function at that point, at that node for the data that it has. Okay. Now, I think the last part of this talk is what we call the regularization of deep learning. So as we saw, which is related to the training these models. As we saw, these deep learning models, they're very complicated. They have a lot of parameters. So due to this large number of parameters and their complicated, semi-complicated architecture, this DAC, it is prone to what is called overfitting. And overfitting, we'll see in other tutorials a little bit more of the theory behind it, but basically describes the situation where the model is over-optimized to accurately predict your training data at the expense of generalizing to unknown data. So for example, assuming that you have training data that look like the points in the graph here, like the black points, and assuming that you have a lot of them, like here, more than what we have here, the deep learning model can learn a function that really accurately follows this data that looks like the blue one. But then, assuming that this data, is noise coming from a linear function, you'll see that for unknown points, the model can make a larger errors than a smaller a model that will learn this latent linear function. Okay, so this is what we call overfitting. So basically, in the term of deep learning, the model learns the noise from the data as opposed to the underlying function that describes the data. Okay. Now, and this is as we said, is proven is a big problem in deep learning. Like dealing with this is part of is not part of like you should do it, but it's part of you have to do it. Okay. Now, here I have a technique, not only regularization techniques, but all the techniques that are usually used in order to mitigate the problem. One is to train with more examples. So you try to actually overcome the complexity of the model, to find a simpler model, for example, with less hidden layers or with fewer nodes per layer, and so on and so forth. You can add some statistical noise to the inputs during training so that the model learns how to recover from that noise. To include regularization terms in the loss function, which is also part of regularizing classical models. So for example, main thing is penalize the model during training based on the magnitude of the weights, and popular regularization functions are L1 and L2. Okay. So basically, you try to suppress these models, and depending on which one you have, to suppress the weights of the models. You try to learn smaller values for this, and depending on which you have L1 or L2, it actually suppresses more or less. Okay. Another technique that is tied is more tied to the deep learning model is what is we call dropout, and which basically does is probabilistically remove some of the inputs during training. Inputs here, it's actually not a good word because it can remove any node in the network. So probabilistically can take, while it's training, at every step of the training process, it can remove some of these, some of the nodes, both usually at the hidden layer. And the intuition for this is that then the node learns not to depend on the other nodes to make a decision. Another one is to use early stopping, which is to monitor the performance of a known set and see when this, and stop when see that the performance degrades. In this case, you have your training data, which you use in order to train the model and find the weights, but you also have set aside a validation set, which the model does not see it when changing the weights, and you only use it in order to test this performance degradation or not. And another one, which is not tied to regularization per se, but has a regularization effect, is what is called batch normalization. Okay, in this, at each step of the normalization, of the train process, you transform the values that you got so that the means, the means and variances of the weights at each layer is remaining the same at every step. Okay, and this has some small regularization effects. So batch normalization, although it's not used for this particular one, it does have. Okay, and before finishing, here is, do you have any questions on the regularization of the training, wholesale or deep learning? No, okay. And before I finish, I have some, that almost concludes the overview of the deep learning models and how you train them, what are the steps to follow in order to train these models. And here I have some, as I said, examples of popular deep learning toolkits and libraries. Very prominent of them is TensorFlow and PyTorch. Like, you'll see a lot of deep learning models being created using these libraries. And now, depending on your needs or the infrastructure of the organization that you work, you might use some other ones, which are not even in the list. And that actually concludes the first part of the tutorial, and we can have some questions here, and we'll have a very short break. If anybody has any questions, I will stop sharing for a moment.
Maybe a very general question, and feel free to defer. So I'm curious about how you select the model. So is it when you have a particular task that you want to solve, you first look in the literature for the types of models that have been used, so the types of networks and so on, and then you experiment around? So it's kind of trial and error, or do you build up intuition for what you want to capture and then you write that network?
Right. That's a very good question. It doesn't have a good answer. It has a general answer. It depends on the problem. It's not only, but you should not also, for deep learning, the difference between from classical machine learning is that you might not even build your model from scratch. You might actually get an architecture that somebody else created in a library. And not even that, you might actually get what we call pre-trained models that somebody has created an architecture, and from the literature, you know that it performs well. For specific problems, like for example, image processing, there are well-known models, and we'll see examples of this in different tutorials. And on top of that, it has done some general training. So you start from that. And that becomes even more profound in other models, like even more complicated, like models that are used in NLP, like transformer-based, like BERT or so on, which with training from scratch. Their architecture is not that hard to create, but training from scratch needs so much data that it becomes, depending on where you're based, what is your organization, what are your resources, becomes impossible. Okay. Now, for cases though where we have multi-layer perceptrons and we have the problems, as we said, the structured data, then, and we'll see there, creating a multi-layer perceptor is a matter of 3 or 4 lines of code. Then you can actually play with your architecture. And as you saw, the architecture, the decisions that you will make there is what is the number of layers, what is the size of its layer. So you can play. But it's also, so as I said, it depends on the problem. Okay. Any other questions?
Thank you.
Welcome.
Yes. Hello.
Hello.
Thank you for the presentation. I'm doing my research in the financial sector, and in the banking industry, we have lots of data and complicated problems for which I think neural networks might be a good fit. But we have also lots of constraints by GDPR and by regulator that impose to have some explainability, like how the model learned and why it gives a certain output. And I was wondering if you were doing some research on that, or if you have some guidelines on how to achieve this explainability.
Okay, that's a good question. Now, myself, I do not do much research there. But I'll give you a general answer, and feel free to reach out more for to diiP or to like by email in order to give you more references. But for my view, there are 2 different kinds of techniques that I've seen in deep learning and machine learning in particular. One is that you try to explain the output of their models, but this depends whether you can, what I call change the model or calibrate the model to give. For example, assuming that you are doing image processing and you have a convolution neural network, like a image classification, then there are techniques in order to tell you, for this particular answer, these parts of the image have been described. That is the one. So you basically change your model. So you have, it is what we call, or some people call opening the model. Okay, but so this depends really on model by model. Now the other ones that they're what's called more like black box techniques that are based more on the counterfactual causality, basically theory, where it's trying to use some metrics, like for example, the I think in economy you use a lot the, actually I don't remember the names now anyways, which tries to find which of the input has an effect on the particular output of the model. And you can do causality theory there, because you can basically have what if scenarios, like you can say change the value of the input in order to see what is the value of the output.
Yeah.
Shapley score, that's one that basically you. Now for this, there is some work, but it's not sure how this is extended, for example, to models that handle unstructured data, like images. you can assume how I can change my numbers, like if you have, for example, input, a numerical input, but how you're going to change, how you're going to do this counterfactual when you have text, or when you have signals like sound, or when you have images. Okay.
Yes, thank you. Thank you.
Actually, one more comment on this subject. You may be interested in a diiP seminar that we're going to have on October 6th on explainable and fair AI. So we will announce this, I guess, after the summer.
Sure, that'd be very interesting. Yeah.
Any other questions? Okay, so I'll stop sharing. Let's see what is the time. Oh, we did get 1 hour. If it's okay, let's have 2 minutes break. And we'll go the last part, which is the kind of a demo or an example, will be quite short. So like 10, 15 minutes, I would say. Okay, so let's continue with the demonstration. So for this one, I decided to keep it fairly simple. It will be, because we talked about multi-layer perceptron, so it will be a small two examples of how to perform and how to go to build a multi-layer perceptron using, I will use Python here, and one of the libraries actually. And I'll use a TensorFlow Keras, which is a library, more higher level library on top of TensorFlow. And I will start sharing my screen. Okay. So first example is a classification example. So we have this data come from the UCI data mine archive. The one that I'm using is the sonar dataset, which is a dataset that describes sonar chip returns bouncing off different services. So basically we have 60 input variables that describe the strength and returns at different angles. And the label is that using these variables, we try to decide, to predict whether what is hit is a rock, we call that R, or a metal. Okay. So this is a binary classification. That means that we have two classes, the rock and R and M, we'll call it R and M. And classification is because we are trying to identify the label of this. Okay. So first thing is that we load the data. Here it is using what is called a pandas library, which is, you can think of it as an abstraction of a table. So loading the data, actually, let me also run it. So I have the data in a file system, which is called, in a file it's called sonar.csv CSV file. It's loading the data, and it's loading in this table that it's called sonar_dt. So the first, the first 60 columns is the attributes that we said. So this is our input, this is our independent variables. And the last column, the column 60, it shows the label of that, whether it is a rock or metal. Okay. So let me move it a little bit here so I can move that. Now, having the data in this format, we need to do some pre-processing. So a multi-layer perceptors understand numbers as input. As we said, a tensor, it gets numbers. So the first thing we need to do is to change the label of the output variable, which now is a string, is a character from R to M, to a number, to a numerical value. So we'll use here 0 or 1. Okay. And that's basically what it's doing here. The first one, can you see my highlighting? I'm not sure about that. Yeah. Yes. Okay. So the first one is getting the the input that we have in this table, and it divides into the first 60 numbers. Columns, and it also makes it floating, just in case there are some errors there, and also it divides also the last column. Okay, and then the next part here is basically encoding the R to M in integer variables 0 and 1. Okay, so that's basically here. Oops, sorry, that was here. So that's what it did. And let me see if I can do something. If we see here now, this which is the array that keeps our dependent variable, you see it changed it from R to M to 0 and 1s. Okay. Now we create the model. And as we said here, we are going to use a multi-layer perceptron. This is, and we are going to use Keras in order to, the Keras library in order to create that. Now, Keras defines what is called a dense layer. Always is good to think of the abstraction of the deep learning as layers. So a dense layer here is one layer in the directly acyclic graph that we saw. And also it has a particular layer which is called input in order to create your input tensors. Okay. So in this case, this function here creates the model. You have to define the model. Then you define the layer, which is the input layer. And what you need to give here is the dimensionality of this, which is the number of variables, the 60 variables that we have. Then I decide that my model is going to have an input layer, a hidden layer, and output layer. Which the output layer, because it's a classification, it has to return either a 0, 1 or a probability that we described. Okay, so the input layer here as we described. The hidden layer is again a multi-layer perceptron. It is a set of perceptrons. And what I say here is that the input the input dimensionality of this layer is equal to the input, the output of the layer is equal to the input. So here I create as many perceptrons as the dimensionality of the input. And also I say that the activation of every perceptron is ReLU, the activation that we described. And then the output layer is a layer that, again, a dense is a set of perceptrons, but because it is just one number, is one perceptron, that's why it says 1. And the activation that I use is sigmoid. You could use anything else that would return a binary variable. Excuse me. Now, and here is once you define the model, you compile the model. That means that you say to the library, create the internal structures in order to define the model. It also, you can also describe, in order to train it, what is the loss function that you are going to use. We're going to use binary cross entropy, as we discussed. The optimizer is Adam, is a variation of the gradient descent, and also as metric, in the accuracy metric, you can always output the loss, but the loss might not be very informative to you. Like the loss is going to be the output of the cross entropy, might not say something. So we define also the accuracy, which is how many labels it has predicted correctly. Okay. And now, well, the rapid doesn't matter that much. I will explain, but when we run that, just we see. Here, basically, when we define the model, we didn't actually say for every layer, we defined what I call the template of the model. Like we defined in terms of layer, how many perceptrons to create at each layer, how many layers we'll have, so on and so forth. And what it does then, it creates all these matrices that we solve, the weight matrices that we'll need to compute during training. And as we say here, as output, it gives you how many parameters it created based on your input. That is how many weights you have. And out of this, how many trainable parameters are. That means that during training, the model will identify values for this. It will, so these parameters will participate in the training. The reason for this is sometimes you can decide that some of them are not going to be, you don't want to change them. For example, as we described, when you have a pre-trained model and you want some of these parameters not to be changed. Okay. Now, another thing is that sometimes you might need to do further pre-processing. For example, if you have images, you want to standardize them, or you might decide that you want a logarithm of something. Here I do standardize them, although I don't think we need, because it's a 0-1. So I just do some pre-processing, and then here I train the model, train the model. And interesting here is in order to train the model is using what is called stratified k-fold. That means, remember that we said that what we want to do is that at every step we want to have a training test, and we want to have a validation test in order to be able to check this accuracy. Now, if we have enough data, we can have these two validation training sets separate. But it might be the case that you don't have enough data. So what you want to do is that you still want to have to be able to validate it, but you also want to use as many training examples as possible. So one of the ways to do it is that at every step you partition the data on randomly somehow on a test and a validation. And that's basically this cross validation. And here it is trained, and we see that our classifier, it gives you the results, which is what we define, the accuracy here. So it gives you the mean accuracy for how many times we run it, as well as the standard deviation. So it's around 87%. Okay. Any question here? That's a basic model to perform the classification. Now, going to the question that we get, okay, what if we don't like this model? Like we want to tune the model, we want to change the architecture. So same thing here, does the same, except now that the hidden layer that we have, it has a smaller, it outputs a smaller number of units. So the only thing we change is that I have my input layer, my hidden layer, my out layer, and the only thing I change is the input, and I say that instead of input dimension that I had before, I do it the I output, I have only half of the value of this. And running it, let's see how much. Why would you need a simpler model? Again, as we said, we might find that it overfits. So let's see what we'll get here. Oops, here. So it's running. Let's see, before we found 87.5. Here, it'll take a little while, but it's not taking that much. It will finish in. Okay, and while we wait for that, let's see the third one is here. I decide that I'm actually going to have, you know what, I'm going to have more hidden layers. And the only difference is adding 2 hidden layers, input and output the same, 2 hidden layers. So here the output, it came is 85%, a little bit worse than what we had before. And here the only difference is here. And the other things you can change, as we said, is the activations, is the dimensionalities. Well, yeah, that's basically what you need. And also the hyperparameters, which is instead of using Adam optimizer, use something else. Is the metric that you, although that does not change the training, but you might decide that I'm going to use a different metric for accuracy. It might indirectly affected because you're using this in order to decide on the if you're going to do a early stopping, and we run that as well. So while we wait that, the one thing I want to say about the keras, now we started with the keras library, which is, as I said, the library, high-level library on top of TensorFlow, is that the way you define the model is pretty much like that. Now, I haven't gotten into details on how you can define a train. Here I used libraries, and we'll see that in the other tutorials. Now, if you have, for example, other types of neural nets, for example, you want to add a convolutional or a sequential neural network, it will be pretty much the same with the sequential. And the sequential, basically what it means, there are 2 different graphs that they have there. The sequential means that every, what is called, every input that you defined is before in your graph of the, input every layer. So the input layer that you have there is in sequence with the other layers. Now you can also create a more general structure, for example, a graph. It's a little bit different API for that. And here I ran and gave 86%. So that is the example of the classification. So if you have any questions here, I think this code and the slides will be shared online if you want to play with this as well as where to get the data. And very fast, what changes if we want to do a regression example? So for regression, what I'm using is what is called the Boston housing prices. So you have houses in the Boston area. It's kind of a well-known data set that have different characteristics, and you try to predict their price. So if we run that, the 14th column is the price. Same thing here, we load the data. Do the partition that we described. Okay, and we define the model. And the only difference here would be, well, assuming that you're going to have 3 layers, is what we need to define is, you see, I don't give a activation function for the output, but it is directly the weighted input, the weighted output of the previous layer. Okay. Other than that, the loss is a mean square, and the optimizer is Adam. Now, initializer here, I didn't describe that, is that because you learn the model, you learn the weights of the model, you have to start from somewhere. So one way is to put some static values, like you initialize your weights to 0, might not be a good idea. So basically what this does is that it initializes the weights in using a Gaussian. Okay, run it. Sorry, compiling it, and again it has 3 layers: input, hidden, and the output. Okay, and again some standardization if it's needed. Now the pre-processing, I'm going to get into these details because this really depends on the data, what kind of pre-processing you want to do. Okay, and then we run, and again we use here, run the model, we use again the mean square error as our accuracy measure. Now, how good is this? The regression is a little bit harder. So usually what you do is that you define a baseline model. It's always the case, not only for regression, but starting with a baseline model, you want to see how much better you are from that. Okay. Classification is a little bit, the accuracy is made a little more intuitive sense. For example, when you say 85%, it says that in this case, it was 85% correct. Well, a number that we'll get here might not be too intuitive, like it might 3.8, what does this mean? Okay. And while we wait here, if you have any questions, because that's the end of the demo also. Wow, okay, you did things, so, and that we get the answer of this. And that concludes my presentation. If you have any final questions, I will be happy to take them. Otherwise, I would like to thank you again for being here, and have a good afternoon. Goodbye, everybody.
Thank you.
Thank you.